Hello, in this lecture we'll answer two questions. In the first question we find out they have this pentagon A, B, C, D, E, and in the second question we find out they are this green shape. So we start with the first question. The following we have pentagon A, B, C, D, E. So what is a pentagon? A pentagon is a flat closed shape with 5 straight sides and 5 interrogers. This is pentagon A, B, C, D, E. It has 5 sides, 1, 2, 3, 4, 5, and 5 interrogers. 1, 2, 3, 4, 5. So, in the drawing, we have pentagon A, B, C, D, E. In addition, we know that those two angles are both right angles. This is side ED, this is equals to 1 unit in its length. Side DC equals to x units in its length. Side CB equals to 1 unit in its length. Side AB equals to 1 x units in its length. And side EA equals to 1 unit in its length. Again, our task is to find out they have this pentagon A, B, C, D, E. So first of all, we join points E and B together by a straight line. And we join points E and C together by a straight line. The next step, we will extend side BA of this pentagon ABCD by a straight line in such a way that the extended part will be equal to x units in its length. We define this point as point M. This is the extended part AM that is equals to x units in its length according to our construction. AB is one side of a pentagon ABCD, it is absolutely a straight line. We extended the straight line BA by a straight line and we got by a straight BM. When we extend the straight line by a straight line, the result BM is also a straight line. So if we focus on the upper side of the straight line BM at point A, here the sum of the areas must be equal to 180 degrees according to all three. All three states that the sum of the areas on one side of a straight line is equal to 180 degrees. So which areas we have at the upper side of the straight line A and B at point A? We have this angle that is right angle, plus this missing angle. In total the sum of those two angles must be equal to 180 degrees according to all three. Therefore, this missing angle must be equal to 90 degrees in its size. In the next step, we join points E and M together by a straight line. By joining points E and M, we can get the right side EAM. In the next step, we will prove that those two right angles can go into each other according to side angle side rule. So again, we prove that this right angle EAM can go into this right angle EDC according to side angle side rule. So therefore, to prove that the right angle EAM can go into this right angle EDC according to side angle side rule. So why those two right triangles can go into each other? First of all, those two sides, they are both equal to x and therefore they are equal to each other. That is to say, side AM of the right triangle EAM is equal to side DC of this right triangle EDC. And again, side AM of the right triangle EAM is equal to side DC of the right triangle EDC. They are both equal to x and therefore they are equal to each other. In addition, those triangles are both equal to 90 degrees and therefore they are equal to each other. So here this is again EAM. In the right triangle EAM, and it is equal to this angle. This is actually again EDC. In the right triangle EDC. Repeat again. Angle EAM in the right triangle EAM is equal to angle EDC in the right triangle DEC. They are both equal to 90 degrees and therefore they are equal to each other. And finally, those two sides, they are both equal to 1 unit, to 1, and therefore they are equal to each other. So actually this is side EA. In the right triangle EAM, and is equal to this side, that is side ED, in the right triangle EDC. Repeat again. Side EA in the right triangle EAM is equal to side ED in the right triangle EDC. They are both equal to 1 and therefore they are equal to each other. So if you found out that those two sides and the angle that is included between those two sides, that is angle, right angle, in the right triangle EMA are correspondingly equal to those two sides, and the angle that is included between those two sides, that is a right angle, in the right triangle EDC. And therefore, to prove that those two right angles can go into each other, according to side angle side rule. We have those two sides, and the angle between those two sides and the right triangle EAM are correspondingly equal to those two sides and the angle that is included between those two sides in the right triangle EDC. And therefore, those two right angles can go into each other according to side angle side rule. So right now we should found out that the right triangle EAM can go to the right triangle EDC according to side rule. So this is the right triangle EMA. It's going to this right triangle EDC according to side angle side rule. And from the fact that those two right angle triangles can go into each other, we will derive that they have also the same areas. That is to say, the area of this triangle EMA is equal to the area of this green right triangle EDC. So write it down, and we found out that the area of the right triangle EAM is equal to the area of this right triangle EDC. And again, from the fact that those two right green triangles can go into each other, we derive that they are also the same areas. That is to say, the area of the right green triangle EAM is equal to the area of the right green triangle EDC. So, if we define the area of this green right triangle EAM is Z, that is to say it is equal to Z square units in its size. Then the area of this right green triangle EDC must be also equal to Z square units in its size because they can go into each other. And the second thing that we derive from the fact that those two right green triangles can go into each other, we derive that side EC of the right green triangle EDC is equal to side EM of the this green right triangle EAM. Why? Because according to the rule that corresponding sides in congruent triangles are equal to each other. Those two right green triangles can go into each other, and therefore the two corresponding sides, that is to say EC and EM, must be also equal to each other and their lengths. So EM equals to EC. EM equals to EC. In the next step, we will calculate the length of line segment MB or side A MB. MB in total equals to MA plus AB. So already know MB in total equals to MA plus AB. So MB in total equals to MA, that is X, plus AB, that is 1 minus X. So in total MB equals to X minus X, that is 0. So we're left only with 1. MB equals to 1 unit in its length. So this is side MB. Is equal to 1 unit in its length. In the next step, we will prove that triangle MEB can go into triangle EBC according to side rule. Okay, again we prove that triangle MEB can go into this triangle EBC according to side rule. So triangle MEB can go into this triangle EBC according to side rule. So why those two triangles can go into each other? First of all, those two sides, they are both equal to 1 and therefore they are equal to each other. So this is side MB of triangle MEB is equal to this side BC on this side EBC. And again, side MB of the right triangle of triangle MEB, it is not a right triangle, is equal to side BC of triangle EBC. They are both equal to 1 and therefore they are equal to each other. In addition, we already found out that those two sides are equal to each other. Those two sides are equal to each other. That is to say, EM equals to EC. Again, EM equals to EC. Side EM of the right triangle MEB is equal to side EC of the right triangle EBC. EM equals to EC. And finally, this is side EB. That is a common side that belongs to both triangles. Side EB belongs to triangle BEC, and side EB also belongs to triangle BEC. So I can write down that side EB equals to itself. It's a common side that belongs to both triangles. Read again. Side EB equals to itself is a common side that belongs to both triangles. So if we prove that all the three sides of this triangle MEB are correspondingly equal to all the three sides of this triangle EBC. And therefore those two triangles can go into each other according to side rule. So I write it down. If you found out that triangle MEB congruent, this is the sign of congruent, to triangle EBC according to side rule. And from the fact that those two triangles can go into each other, we will derive that they have also the same areas. That is to say, the area of this triangle EMB is equal to the area of this triangle EBC. Any two triangles that can go into each other, they must have also the same areas. So if you found out that the area of triangle MEB is equal to the area of triangle EBC. In the next step, we will calculate the area of this triangle MEB. The area of any triangle equals to the base of the triangle times the height over 2. We choose the base SMB. The height is AE over 2. So in total, we actually found out that the area of triangle MEB equals to the base MB times the height AE over 2. MB is 1 times AE, this is also 1, divided by 2. So in total, we have found out that the area of this MEB is equal to 1 times 1 over 2. 1 times 1 is 1, so total the area of the triangle MEB is equal to 1 half square in its size. So again, if you found out that the area of triangle MEB equal to 1 half square in its size. But we already found out that the area of triangle EAM is equal to the area of triangle EDC. Found out that because of the fact that those two triangles can go into each other, they have also the same areas. So I can write down here that the area of triangle MEB is equal to the area of triangle EDC. And from this equation, the area of triangle EDC equals to the area of triangle MEB equals to 1/2. We will derive that the area of triangle EDC is also equals to 1 square inch in its size. The area of triangle EDC is also equal to 1/2 square inch in its size. So the area of triangle MEB plus the area of triangle EDC is equal to 1/2, that is the area of triangle MEB plus the area of triangle EDC, this is also equal to 1/2. So in total, the sum of the areas of those two triangles equals to 1/2 plus 1/2, that is 1. So the sum of the areas of those two triangles is equal to 1 square inch in size. So what is the area of the big quadrilateral EMBC? The area of the big quadrilateral EMBC must be equal to the sum of the areas of the two shapes that it consists of. The big quadrilateral EMBC consists of those two triangles and not any more things. And therefore, the area of this quadrilateral EMBC must be equal to the sum of the areas of the two triangles that it consists of. That is to say, the area of this quadrilateral EMBC must be equal to the area of this triangle EMB, this is 1/2, plus the area of this triangle EBC, this is also 1/2. So in total, we found out that the area of the big quadrilateral EMBC is equal to 1/2 plus 1/2, that is 1. So in total, the area of the big quadrilateral EMBC is equal to 1 square inch in its size. But the big quadrilateral EMBC consists also other two shapes. It consists of this ring triangle EMA, and it also consists of this quadrilateral ABCE. Therefore, the area of the big quadrilateral EMBC must be equal to the sum of the areas of the two shapes that it consists of. So also other shapes. The big quadrilateral EMBC consists of this ring white triangle EMB, and it also consists of this quadrilateral ABCE. And again, the area of the big quadrilateral EMBC must be equal to the sum of the areas of the two shapes that it consists of. That is to say, it must be equal to the area of the green white triangle EMB plus the area of quadrilateral ABCE. We already found out that the area of the big quadrilateral EMBC is equal to 1. So we can write here that the area of the big quadrilateral EMBC equals to 1. And from this log equation, 1 equals to the area of quadrilateral EMBC and it is also equals to the area of the right rectangle EMB plus the area of quadrilateral ABCE. Those two sides are equal to each other. Therefore, can I know that 1 equals to the area of the green rectangle EMB plus the area of quadrilateral ABCE. So if you found out that the area of this right triangle, it is the right triangle EMA, the area of that right triangle EMA plus the area of this quadrilateral ABCE in total is equal to 1. The area of the green right triangle EMA plus the area of quadrilateral ABC equals to 1, so it's its size. But according to our definition, the area of the green quadrilateral EMA is equal to Z, so what is its size? So you can substitute the area of the right green triangle EMA by Z, and we get that Z1 equals to Z plus the area of quadrilateral ABCE. So in total we found out that Z plus the area of quadrilateral ABCE equals to 1. And again, Z plus the area of quadrilateral ABC equals to 1. Our task is to find out the area of this big pentagon ABCDE. So what is the area of the big pentagon ABCDE? Actually, the area of the big pentagon ABCDE must be equal to the sum of the areas of the two shapes that it consists of. That is to say, the area of this big pentagon ABCD must be equal to the area of this green right triangle EDC plus the area of this quadrilateral ABCE. Pentagon ABCD consists of those two shapes only and not anything else. Therefore, the area of pentagon ABCD must be equal to the area of this green right triangle EDC plus the area of this quadrilateral ABCE. So right now, the area of the big pentagon ABCD must be equal to the area of this green right triangle EDC plus the area of this quadrilateral ABCE. Okay, again, I should find out that the area of the big pentagon ABCD must be equal to the area of green right triangle EDC plus the area of quadrilateral ABCE. And I already found out that the area of this green right triangle EDC equals to Z, so it's in its size. So we substitute the area of the green right triangle EDC by Z. Plus the area of this quadrilateral ABCE. So in total we actually found out that the area of the big pentagon ABCD is equal to Z plus the area of quadrilateral ABCE. But we already found out that Z plus the area of quadrilateral ABC equals to 1. So I can copy this equation here. Z plus the area of quadrilateral ABC equals to 1, according to what we already found out. And from this long equation, we derive that the area that we are looking for in this question, that is the area of the big pentagon ABCD, is equal to 1 square unit in its size. So we finished with the first question. Repeat again. We actually found out that the area that we're looking for in this question, that is the area of this big pentagon ABCD, is equal to 1 square root in its size. So we finished with the first question. In the next step, I will present you the second question and we solve the second question of this lecture. In the second question, our task is to find out the area of this green shape. The green shape is actually triangle A and B. So we have to find out the area of the green triangle A and B. So it is given us the question that chord AB is the diameter of the circle. We also know that line segment AP equals to 9 units in its length. This is line segment BQ. This equals to 4 units in its length. PQ is tangent to the circle at point M. Those two angles are both right angles. Again, our task is to find out the area of this green shape. That is actually triangle A and B. The triangle A and B. It is given as the question that AB is the diameter of this circle. Chord AB is the diameter. So I write down that AB is the diameter of this circle. So here we can implement rule 7 in our drawing. I click quickly on rule 7. According to rule 7, if a peripheral angle subtends on the diameter of the circle, then it is equal to 90 degrees in its size. In the drawing we have a circle. This is called AB, that is the diameter of this circle. This is peripheral angle ACB that subtends on chord AB, that is the diameter of this circle, and therefore according to this rule 7, peripheral angle ACB must be equal to 90 degrees in size because of the fact that it subtends on the diameter of the circle. Therefore, according to this rule, any peripheral angle that subtends on the diameter of the circle must be equal to 90 degrees in its size. This is peripheral angle A and B that subtends on the diameter of the circle. That's what we call AB, and therefore it must be equal to 90 degrees in its size according to rule 7. In the next step, we will define angle PAM. This angle is alpha. So in the right triangle APM, this angle equals to alpha. This angle equals to 90 degrees, and therefore this third missing angle must be equal to 90 degrees minus alpha. Why? Because 90 degrees minus alpha plus alpha is 90 degrees, and 90 degrees plus 90 degrees, it is equal to 180 degrees. That is the sum of the angles in any triangle. PQ is a tangent to the circle at point M, therefore PQ is a tangent, it is absolutely a straight line. So if we focus on the upper side of the straight line PQ at point M, here the sum of the angles must be equal to 180 degrees according to rule 3. Rule 3 states that the sum of the angles on one side of the straight line is equal to 180 degrees. So each angle, we have the upper side of the straight line PQ at point M, we have this angle is equal to 90 degrees minus alpha, plus this angle equals to 90 degrees in size, plus this angle BMQ. In total, the sum of those three angles must be equal to 180 degrees according to rule 3. So is enough. So we should find out that 90 degrees minus alpha plus this angle that is equal to 90 degrees in size plus this angle BMQ. In total, they must be equal to 180 degrees in their sizes, according to all three. In this set of the equation, we have 90 degrees plus 90 degrees, it is 180 degrees. Plus the missing angle BMQ minus alpha is equal to 180 degrees. Here we have 180 degrees on both sides of the equation, so 180 degrees will get cancelled, and we left only the missing angle BMQ minus alpha equals to 0. Here we add alpha to this equation, and when we get that the missing angle BMQ is equal to alpha degrees in its size. This is the missing angle BMQ is equals to alpha degrees in its size. So in this small right angle BMQ, this angle equals to alpha, this angle equals to 90 degrees, and therefore this third missing angle must be equal to 90 degrees minus alpha, according to the rule that states that the sum of the angles in a triangle is equal to 180 degrees. It is very easy to see that those two right angles are similar to each other according to angle similarity rule. So when those two right angles are similar to each other. First of all, those two angles are both equal to alpha and therefore they are equal to each other. In addition, those two angles are both equal to 90 degrees and therefore they are equal to each other. And finally, those two angles are both equal to 90 degrees minus alpha, therefore they are equal to each other. So we should find out that all the three angles of this big right triangle APM are correspondingly equal to all the three angles of this small right triangle BMQ. And therefore, those two right triangles are similar to each other according to angle similarity rules. So I'll write it down. We should find out that the big right triangle APM is similar. This is the sign of similar to the small right triangle BMQ according to angle similarity rule. And from the fact that those two right angles are similar to each other, we will derive that the following relationship exists between their sides. We will derive that side AP of the big right triangle APM over side MQ of the small right triangle BMQ is equal to side PM of the big right triangle APM over side BQ of this small right triangle BMQ. If you get from the fact that those two right triangles are similar to each other, we derive that the following relationship exists between their sides. We derive that side AP the side AP of the big right triangle APM or side MQ of the small right triangle BMQ is equal to side PM of the big right triangle APM or side BQ of the small right triangle BMQ. AP is 9 over MQ. MQ is the missing side, so leave it as it is. And it is equal to PM. PM is the missing side, so leave it as it is. Over BQ. BQ equals to 4 units in itself, according to what is given as the question. So in total, we found out that 9 over MQ equals to PM over 4. Here we'll cross multiply this equation. And finally, we get that 9 times 4, that is 36, is equal to PM times MQ. And again, we found out that PM times MQ equals to 36. In the next step, we will define the center of this circle. This point is point O. So OA is the radius of the circle. We define the radius of the circle itself. So OA is the radius of the circle. That is equal to 1 according to our definition. OB is also the radius of the circle. That is equal to 1. In the next step, we will join points O and M together by a straight line. Point M is the point of tendency obtained at PQ with this circle. Point O is the center of the circle. Point M is the point of the circle itself. Therefore, OM is the radius of the circle that is equal to R. So here we can implement rule 1. Because here the radius OM that is equal to R. The radius OM is drawn to point M, that is the point of tendency obtained at PQ with this circle. And whenever you have a radius that is drawn to the point of tendency, then tangent PQ will be perpendicular to the radius MO. If PQ is perpendicular to MO, it means that this angle equals to 90 degrees and this angle also equals to 90 degrees according to rule 1. In the next step, we will do a construction, that is to say from point O, that is the center of the circle, we will draw perpendicular on AP. Again, from point O, we will draw perpendicular on AP. So actually, this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. We define the touching points of the perpendicular from point O inside AP. This point is point L. By doing this construction, we get the big quadrilateral LOMP. Inside the big quadrilateral LOMP, we have 1, 2, 3 rectangles. The sum of 3 rectangles is equal to 270 degrees. So 270 degrees plus the size of this fourth missing angle, in total the must be equal to 360 degrees. according to the rule that states that the sum of the angles in any quadrilateral is equal to 360 degrees. And therefore this fourth missing angle must be equal to 90 degrees in its size. So in the big quadrilateral LOMP we have 4 right angles, and according to rule 5, any quadrilateral that has 4 right angles must be at least a right angle if not a square. So we relate to quadrilateral LOMP as a right angle because it has 4 right angles. In the next step, we do another construction. This is to say, from this point B, we will draw perpendicular on the radius OM. Again, from point B, we will draw perpendicular on the radius OM. So actually, this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. We define the touching point of the perpendicular from point B and the radius OM. This point is point S. By doing this construction, we can do the small quadrilateral SBQM. Inside the small quadrilateral SBQM, we have 1, 2, 3 right angles. Therefore, this fourth missing angle must be equal to 90 degrees in its size. And therefore, the small quadrilateral SBQM is a right angle because it has 4 right angles. So, as you know, the small quadrilateral SBMQ is a right angle. According to rule 5. We know that the opposite sides of a rectangle are parallel to each other. Okay, again, the opposite sides of a rectangle are parallel to each other. So in the big rectangle LOMP is a rectangle according to what we have found out. So in the big rectangle LOMP, the side LP is parallel to the opposite side OM. Again, LP is parallel to OM. But LP is part of the straight line AP. And if a part of the straight line is parallel to another straight line, then the straight line AP itself must be also parallel to the other straight line OM. So I should find out that AP is parallel to OM. So, AP is parallel to OM. In the next step, we copy the two parallel lines AP and OM and the diameter AOB in a new page, and we implement rule 50 in the new drawing. So actually, those are the two parallel lines AP and OM. This is the diameter AOB, the point from the original drawing. Those two angles are defined as corresponding angles, and they are located between the parallel lines AP and OM, and therefore they are equal to each other in their sizes, according to Rule 50. Right, Rule 50. According to Rule 50, corresponding angles between parallel lines are equal to each other. In the drawing you have line A that is parallel to line B. The red line C cuts those two parallel lines at those 2 points. Those two angles, alpha and beta, they are defined as corresponding angles, and they are located between the parallel lines A and B. Therefore, they are equal to each other in their sizes according to this rule, Rule 50. That is to say, alpha equals to beta. So, those two angles are defined as corresponding angles, and they are located between the parallel lines AP and OM, and therefore they are equal to each other in their sizes. So if we define the size of this angle as beta, then the size of this angle must be also equal to beta, because they are equal to each other according to Rule 50. So in total we found out that angle PAO equals to beta, this angle PAO this is angle PAO is equals to beta. Angle PAO equals to beta. Likewise, we also found out that angle MOB also equals to beta. So actually, this is angle MOB equals to beta. So in this green triangle OSB, this angle equals to beta. This angle equals to 90 degrees, and therefore this third missing angle must be equal to 90 degrees minus beta, according to the rule that says that the sum of the angles in any triangle is equal to 180 degrees. Likewise, this triangle ALO, the right triangle ALO, this angle equals to beta. This angle equals to 90 degrees, and therefore this third missing angle must be equal to 90 degrees minus beta, according to the same rule. It says that the sum of the angles in any triangle is equal to 180 degrees. The next step we prove that those two triangles can go into each other according to side angle rule. That is to say that the right triangle A and O can go into this right green triangle OSB according to side angle rule. So we have to prove that the right triangle A and O can go into this green right triangle OSB according to side angle rule. So why those two right triangles can go into each other? First of all, those two angles are both equal to beta, and therefore they are equal to each other. So here this is angle LAO, in the right triangle AO, and it is equal to this angle, this is angle SOB, in the right triangle OSB. So again, we should hold on that angle LAO in the right triangle ALO is equal to angle SOB in the right triangle OSB. They are both equal to beta, and therefore they are equal to each other. In addition, those two sides, they are both the radius of the circle, and therefore they are equal to each other. This is to say, side AO of the right triangle ALO is equal to side OB of the right triangle OSB. And again, if you found out that side AO of the right triangle ALO is equal to side OB of the right triangle OSB. They are both the radius of the circle is equals to R, and therefore they are equal to each other. And finally, those two angles are both equal to 90 degrees minus beta, and therefore they are equal to each other. So this is angle AOL. In the right triangle ALO, and it is equal to this angle. This is actually angle OBS. In the right triangle OSB. So repeat again, I should find out that angle AOL in the right triangle ALO is equal to angle OBS in the right triangle OSB. They are both equal to 90 degrees minus alpha, and therefore they are equal to each other. So if you found out that those two angles and the side that is included between those two angles, that is R, in the right triangle ALO, are correspondingly equal to those two angles, and the side that is included between those two angles, that is also R, in the right triangle OSB. And therefore those two right triangles can go into each other according to angle, side, angle rule. We have those two angles, and the side that is included between those two angles in the right triangle ALO is also equal to those two angles, and the side that is included between those two angles is R in the right triangle OSB. And therefore those two right triangles can go into each other according to angle, side, angle rule. So I write it down. We actually found out that the right triangle ALO congruent, this is the sign of congruent, to the right triangle OSB according to angle, side, angle rule. And from the fact that those two right triangles can go into each other, we derive that side LO of the big right triangle ALO is equal to side SB. Derive that side LO, the right triangle ALO is equal to side SB in the right triangle OSB. So LO equals to SB according to the rule that corresponding sides in congruent triangles are equal to each other. Those two right triangles congruent to each other, and therefore the two corresponding sides, that is to say LO and SB, must be also equal to each other in their lengths. LO equals to SB. So if we define the length of side LO as x, then the length of side SB must be also equal to x, because they are equal to each other. We also know that the opposite sides of a rectangle are equal to each other. So in the big rectangle LOMP, side LO must be equal to the opposite side PM. But LO is x, therefore the opposite side PM must be also equal to x units in its length. Likewise, according to the same rule, in the small rectangle SBQM, side SB must be equal to the opposite side MQ, but SB equals to x, and therefore the opposite side MQ must be also equal to x units in its length. We already found out that PM times MQ equals to 36. PM times MQ equals to 36. And again, we already found out that PM times MQ equals to 36. PM is X, MQ is also X. MQ is X. So in total we found out that X times X equals to 36. X times X equals to 36. X times X is X squared equals to 36. Here we'll take a root out of this equation and find out that X equals to the square root of 36, that is 6. PM equals to X and X equals to 6. Here we have MQ is equals to X is equals to 6. In the next step, we'll implement the Pythagoras theorem on this small right triangle BMQ. According to the Pythagoras theorem, in any right triangle, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. Here by PT is the relation for Pythagoras theorem. So in this right small triangle BMQ, BM squared, that is the square of the hypotenuse, equals to BQ squared plus QM squared. So write it down. BM squared equals to BQ squared plus QM squared. And again in the right hand BMQ, according to the Pythagoras theorem, PM squared, that is the square of the hypotenuse, equals to BQ squared plus QM squared. BM is the missing side, so it is. So it is BM squared equals to BQ squared. BQ is 4, therefore BQ squared is 4 squared, that is 16. Plus QM squared. QM is 6, therefore QM squared is 6 squared, that is 36. So in total, we have found out that BM squared equals to 16 plus 36. 16 plus 36 is 52. 16 plus 36 is 52. Here we take a root out of this equation and finally we get that the missing hypotenuse BM is equal to the square root of 52 units in its length. And again, I should found out that the hypotenuse BM is equal to the square root of 52 units in its length. In the next step, we'll implement the Pythagoras theorem on this big rectangle APM. Here by PT is the relation for Pythagoras theorem. in the right peak time 8 p.m. AM squared, that is the score of the products, equals to AP squared plus PM squared. So write it down. AM squared, that is the score of the products, equals to AP squared plus PM squared. And again in the big right AMP, only to the quadratic one. AM squared, that is the score of the products, equals to AP squared plus PM squared. AM is the missing side, so it is, so it is AM squared equals to AP squared. AP equals to 9, therefore AP squared is 9 squared, that is 81 plus PM squared. PM is 6, therefore PM squared is 6 squared, that is 36. So in total, we have found out that AM squared equals to 86 plus AM squared equals to 81 plus 36. 81 plus 36 equals to 117. Here we take out all those equations and we get that AM equals to the square root of 117 units in its length. So today we found out that AM equals to the square root of 117 and BM equals to the square root of 52. AM equals to the square root of 117 and BM equals to the square root of 52 units in its length. Our task is to find out the area of this green shape. The green shape, it is actually the green right triangle A and B. We know that the area of any triangle equals to the base of the triangle times the height over 2. Therefore, the area of this green right triangle A and B will be equal to the base MB times the height AM over 2. And again, the area of this green right triangle A and B is equal to the base AM is equal to the base MB times the height AM over 2. We already found out that the base MB equals to the square root of 52 units in its length. Times the height MA, we already found out that the height MA equals to the square root of 117 units in its length. Divided by 2. So in total, we have found out that the area of this green shape, that is actually the area of the green right triangle A and B, is equal to the square root of 52 times the square root of 117 over 2. Here we use the algebraic identity that says that the square root of A times the square root of B is equal to the square root of A times B. So according to this algebraic identity, we get that the square root of 52 times the square root of 117 will be equal to the square root of 52 times 117. And we have to divide it by 2. 52 times 117, it is equal to 6084. We have to divide it by 2. The square root of 684 is equal to 78, and we have to divide it by 2. 78 over 2 is 39. So in total, we found out that the area that we are looking for this question, that is the area of the green shape, it is equal to 39 square inches in size. So the area of the green shape, in total, is equal to 39 square inches in size. And again, we found out that the area of this shape, that is the area that we are looking for this question, is equal to 39 square inches in its size. So we finished with the second question. In the next step, I will summarize the lecture. I'll start with the first question, of course. In the first question, our task was to find out the area of this big pentagon ABCD. Repeat again. In the first question, our task was to find out the area of this big pentagon ABCD. What is a pentagon? A pentagon is a flat closed shape with 5 straight sides and 5 interlocks. This is pentagon ABCD. Pentagon ABCD is 5 sides, 1, 2, 3, 4, 5, and 5 interlocks. 1, 2, 3, 4, 5. So this is pentagon ABCDE. We know that those two angles are both right angles. Side ED equals to 1, side DC equals to x, side CB equals to 1, side BA equals to 1 minus x, and side EA equals to 1. Again, our task is to find out the area of this big pentagon ABCDE. So first of all, we join points E and B together by straight line. We join points E and C together by straight line. In the next step, we extended side BA of this pentagon ABCD. We extended side BA by a straight line in such a way that the extended part AM will be equal to x units in itself. Again, okay, the end that AM equals to x units in itself according to our construction. When you extend a straight line by straight line, the result BM must be also a straight line. BM it is absolutely a straight line. AB is absolutely a straight line because it is one side of pentagon ABCD. So BM is a straight line. So if you focus on the upper side of the straight line BM at point A, here the sum of the angles must be equal to 180 degrees according to all three. All three states that the sum of the angles from one side of the straight line is equal to 180 degrees. So which angles we have at the upper side of the straight line BM at point A? We have this angle that is right angle plus this missing angle. In total, the sum of those two angles must be equal to 180 degrees according to all three. Therefore, this missing angle must be equal to 90 degrees in its size. In the next step, we join points E and M together by straight line. By joining points E and M, we created the right green triangle EMA. In the next step, we proved that those two white green triangles can go into each other according to side against side rule. So why those two white green triangles can go into each other? First of all, those two sides are both equal to x and therefore they are equal to each other. In addition, those two angles are both equal to 90 degrees and therefore they are equal to each other. And finally, those two sides are both equal to 1 and therefore they are equal to each other. So I should prove that those two sides and the angle that is included between those two sides, that is a right angle, in this right angle EAM are correspondingly equal to those two sides and the angle that is included between those two sides in this right angle EDC. And therefore those two right angles can point to each other according to side against side rule. Between those two sides and the angle that is included between those two sides in the right entire EAM are correspondingly equal to those two sides and the angle that is included between those two sides in this green right triangle EDC. And therefore those two right triangles can point to each other according to side against side rule. And again, we should remember that the right triangle EAM can point to the right triangle EDC according to we found out that the right triangle EAM can point to the right triangle EDC according to side against side rule. And from the fact that those two right triangles can point to each other, we derive that they have also the same areas. That is to say, the area of the green right triangle EAM is equal to the area of the green right triangle EDC. So if we define the area of this green right triangle EAM as Z, that is to say it is equal to Z squared in its size, then the area of this green right triangle EDC must be also equal to Z squared in its size. The second thing that we derived from the fact that those two right green triangles can point to each other, we derive that side EAC is equal to side EM. Side EC of the green right triangle EDC is equal to side EM of this green right triangle EAM. According to the rule, that corresponding sides in congruent triangles are equal to each other. Those two right green triangles can point to each other, and therefore the two corresponding sides, that is to say EC and EM, must be also equal to each other in their lengths. So those two sides are equal to each other. EC equals to EM. EM equals to EC. In the next step, we calculated the length of side MB. MB in total equals to MA plus AB. MB equals to AM plus MB. So MB in total equals to AM, that is X, plus MB, that is 1 minus X. So in total, MB equals to X plus 1 minus X. X minus X is 0, so left only with 1. So in total, we found out that MB equals to 1 unit in its length. In the next step, we prove that those two triangles can point to each other according to side rule. That is to say, we prove that the triangle EMB can point to this triangle EBC according to side rule. So we have to prove that the right triangle EMB can point to the right triangle EBC. So why those two triangles can point to each other? First of all, side MB is equal to 1 equals to side VC is also equals to 1. Oh, those two sides are both equal to 1 and therefore they are equal to each other. In addition, we already found out that those two sides are also equal to each other. Here EM equals to EC. EM equals to EC. And finally, EB is the common side that belongs to both triangles. EB belongs to triangle EMB and EB also belongs to triangle EBC. So we can write down that EB equals to itself as a common side that belongs to both triangles. So if we found out that all the three sides of this triangle EMB are corresponding equal to all the three sides of this right triangle EBC, and therefore those two, all the three sides of this triangle MEB are corresponding equal to all the three sides of this triangle EBC, and therefore those two triangles can join to each other according to side rule. And then if you know that triangle MEB can join, this is the sign of conjoint, to triangle EBC according to side rule. And from the fact that those two triangles can join to each other, we derive that they are also the same areas. That is to say, we derive that the area of triangle MEB is equal to the area of triangle EBC. In the next step, we calculated the area of this triangle MEB. The area of any triangle equals to the base of the triangle times the height over 2. So the area of this triangle MEB equals to the base MB times the height AE over 2. So again, the area of the big triangle MEB is equals to the base MB times the height AE over 2. And B, we already found that MB equals to 1, and EA is also equals to 1. So MB equals to 1, EA is also equals to 1. And we have to divide it by 2. 1 times 1 is 1 times 1 is 1, so the area of the big triangle MEB equals to 1/2 square in size. In the end, we found out that the area of triangle MEB equals to 1/2 square in size. But we already found out that the area of triangle EDC is equal to the area of triangle MEB because they can join to each other, therefore they are also the same areas. And from this equation, the area of triangle EDC equals to the area of triangle MEB equals to 1/2. We derive that the area of triangle EDC is also equal to 1/2 square in size. So in total, the area of this triangle EBC is equal to 1/2 square in size. So in total, we found out that the area of triangle MEB plus the area of triangle EDC equals to 1/2 plus 1/2, because both areas are equal to 1/2. 1/2 plus 1/2 is 1. So in total, we found out that the sum of the areas of those two triangles is equal to 1 square in size. In the next step, we focus on this big quadrilateral EMBC. What is the area of this big quadrilateral EMBC? Actually, the area of the big quadrilateral EMBC must be equal to the sum of the areas of the two shapes that it consists of. The big quadrilateral EMBC consists of those two triangles, and therefore the area of the big quadrilateral EMBC must be equal to the sum of the areas of those two triangles that it consists of. That is to say, the area of the big quadrilateral EMBC must be equal to the area of triangle EMA plus the area the area of the big quadrilateral EMBC is equal to the area of those two triangles that it consists of. Therefore, the area of the big quadrilateral EMBC must be equal to the area of triangle MEB plus the area of triangle EDC, because it consists of only those two triangles, not anything else. Therefore, the area of quadrilateral EMBC must be equal to 1/2 plus 1/2, that is 1. 1/2 plus 1/2 is 1. So in total, if you know that the area of quadrilateral EMBC equals to 1 square in size. So you can write here that the area of the big quadrilateral EMBC equals to 1 square in size. But actually, quadrilateral EMBC consists of two other shapes. Quadrilateral EMBC consists of this right rectangle EMA and this quadrilateral ABCE. And therefore, the area of quadrilateral ENBC must be equal to the sum of the areas of the two components that it consists of. That is to say, the area of the big quadrilateral ENBC must be equal to the area of this green rectangle EMA plus the area of this quadrilateral ABCE. And again, the area of the big quadrilateral ENBC must be equal to the sum of the areas of the two shapes that it consists of. That is to say, it must be equal to the area of the green rectangle EMA plus the area of quadrilateral ENBC. And from this equation, 1 equals to the area of quadrilateral ENBC equals to the area of the green triangle EMA plus the area of quadrilateral ABCE. We derive that 1 equals to the area of the green triangle EMA plus the area of quadrilateral ABC. Those two sides are equal to each other. That is to say, 1 equals to the area of the green triangle EMB plus the area of quadrilateral ABC. Okay, it is the area of the green triangle EMA, the green triangle EMA plus the area of quadrilateral ABC. So 1 equals to the area of the green triangle EMA plus the area of quadrilateral ABC. But we already found out that the area of this quadrilateral EMA equals to Z. So we can substitute the area of triangle EMA by Z. And therefore in total we get that 1 equals to Z plus the area of quadrilateral ABCD. Repeat again, 1 equals to Z plus the area of quadrilateral ABCE. Our task is to find out the area of the big pentagon ABCD. We have to find out the area of this big pentagon ABCD. Actually, the area of the big pentagon ABCDE must be equal to the sum of the areas of the two components that it consists of. So, the area of the big quadrilateral ABCD must be equal to the area of the first component that is consists of, that is actually the right rectangle EDC, plus the area of the second component that is consists of, that is actually this quadrilateral ABCE. And again, the area of the big pentagon ABCD must be equal to the sum of the areas of that is consists of. Quadrilateral ABCD consists of the green rectangle EDC and the quadrilateral ABCD. Consists only those two components and not anymore. Therefore, the area of the big pentagon ABCD must be equal to the area of the green triangle EDC plus the area of quadrilateral ABC. But we already found out that the area of this green triangle EDC equals to Z squared inside. So we can substitute the area of triangle EDC by Z. So in total, the area of the big pentagon ABCDE is equal to Z plus the area of quadrilateral ABC. But we only found out that Z plus the area of quadrilateral ABCE equals to 1. So you can copy this equation here. Z plus the area of quadrilateral ABCE equals to 1. I copied the equation here. From this page I copied the equation here. So Z plus the area of quadrilateral ABCE equals to 1. And from this wrong equation, we derive that the area of the big pentagon ABCDE is equal to 1 squared in its size. So in conclusion, we found out that the area of the big pentagon ABCD equals to 1 squared in its size. So we finish with the first question. The area of this big pentagon ABCD is equal to 1 squared in its size. So we finish with the first question. In the next step, I will present to you the second question, and I will repeat on the solution that for the second question that we already done. Our task in the second question is to find out the area of this green shape. The green shape is actually triangle A and B. So we have to find out the area of this green triangle A and B. In the drawing we have a circle. We know that chord AB is the diameter of this circle. In addition, we know that PQ is a tangent to the circle at point M. We also know that those two angles are both right angles. We know that AP equals to 9 units in its length, PQ equals to 4 units in its length. Again, our task is to find out the area of this green shape. This is actually the right triangle A and B. Area of the green triangle A and B. So here we can implement rule 7. According to rule 7, any peripheral angle that subtends to the diameter of the circle must be equal to 90 degrees in its size. This is peripheral angle A and B that subtend on chord AB. This is the diameter of this circle, therefore it must be equal to 90 degrees in its size according to rule 7. Peripheral angle A and B equals to 90 degrees. In the next step, we define this angle PAM as alpha. So in the right triangle APM, this angle equals to alpha. This angle equals to 90 degrees, and therefore this first angle must be equal to 90 degrees minus alpha. Why? Because 90 degrees minus alpha plus alpha is 90 degrees, and 90 degrees plus 90 degrees is equal to 180 degrees. That is the sum of the angles in any triangle. So this first angle is equal to 90 degrees minus alpha. PQ is a tangent to this circle at point M. So PQ is a tangent, it is absolutely a straight line. So if we focus on the upper side of the straight line PQ at point M, here the sum of the angles must be equal to 180 degrees according to rule 3. Rule 3 states that the sum of the angles on one side of the straight line is equal to 180 degrees. So for each angle we have at the upper side of the straight line PQ at point M, we have this angle that is equal to 90 degrees minus alpha, plus this angle is equal to 90 degrees according to rule 7, plus this BC angle BMQ. In total, the sum of those three angles must be equal to 180 degrees according to rule 3. Read again, I should found out that in the upper side of the straight line PM at point M, the sum of the angles must be equal to 180 degrees according to rule 3. So 90 degrees minus alpha plus 90 degrees plus the BC angle BMQ in total must be equal to 180 degrees. 90 degrees plus 90 degrees is 180 degrees. So we have 180 degrees plus the BC angle BMQ minus alpha in total must be equal to 180 degrees. Here we have 180 degrees on both sides of the equation, so 180 degrees will get cancelled, and we left only if the BC angle BMQ minus alpha equals to 0. Here we added alpha to this equation, if we found out that the BC angle BMQ equals to alpha degrees in its size. This is the BC angle BMQ that is equals to alpha degrees in its size. So in the small right triangle BMQ, this angle equals to alpha, this angle equals to 90 degrees, and therefore this third BC angle must be equal to 90 degrees minus alpha according to the rule that the sum of the angles in any triangle is equal to 180 degrees. Actually, it is very easy to see that the big right triangle APM is similar to this small right triangle BMQ according to angle similarity rule. That is to say, those two angles are both equal to alpha and therefore they are equal to each other. In addition, those two angles are both equal to 90 degrees and therefore they are equal to each other. And finally, those two angles are both equal to 90 degrees minus alpha and therefore they are equal to each other. So if you found out that all the three angles of this big right triangle APM are correspondingly equal to all the three angles of this small right triangle BMQ. And therefore, those two right triangles are similar to each other according to angle similarity rule. If you found out that the big right triangle APM is similar, this is the sum of similar to the small right triangle BMQ according to angle similarity rule. And from the fact that those two right triangles are similar to each other, we will derive that the following relationship exists between their sides. we derive the side AP of the big right triangle APM or side MQ of the small right triangle BMQ is equal to side QM and side PM of the big right triangle APM or side BQ of this small right triangle BMQ. And again, from the fact that those two right triangles are similar to each other, we derive that the following relationship exists between their sides. We derive that side AP of the big right triangle APM or side MQ of the small right triangle BMQ is equal to side PM of the big right triangle APM or side BQ of the small right triangle BMQ. AP equals to 9 units in itself according to what is given as the question. Or side MQ. MQ is the missing side, so leave it as it is. And this is equal to PM. PM is also the missing side, so leave it as it is. Or BQ. BQ equals to 4 units in itself according to what is given as the question. So in total, if you found out that 9 over MQ equals to PM over 4. Here, of course, multiplying this equation. And finally found out that 9 times 4 is 36, so 36 equals to PM times MQ. In the next step, we define the center of this circle. This point is point O. So OA is the radius of the circle that we define this R. OB is also the radius of the circle that is equal to R. In the next step, we join points O and M together by straight line. Point M is the point of tendency PQ with this circle. So point O is the center of the circle, point M is the point of the circle itself, therefore OM is the radius of the circle that is equal to R. Here we can implement rule 1, well, because according to rule 1, tangent to a circle is perpendicular to the radius drawn to its point of tendency. The radius OM that is equal to R, the radius OM is drawn to point M that is the point of tendency PQ with this circle. And whenever radius is drawn to the point of tendency, then tangent PQ will be perpendicular to the radius MO. If PQ is perpendicular to MO, it means that this angle equals to 90 degrees. This angle also equals to 90 degrees according to rule 1. In the next step, we did the construction, that is to say from point O, we do perpendicular on side AP. Again, from point O, we do perpendicular on AP. So actually this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. We define the touching point of the perpendicular from point O and AP, this point is point L. When we did this construction, we get the big quadrilateral LOMP. In the big quadrilateral LOMP, we have 1, 2, 3 angles. The sum of 3 angles is 270 degrees, so 270 degrees plus the size of this fourth missing angle. In total, they must be equal to 360 degrees according to the rule that the sum of the angles in any quadrilateral is equal to 360 degrees. And therefore this fourth missing angle must be equal to 90 degrees in its size. So in quadrilateral LOMP we have 4 right angles, and according to rule 5, any quadrilateral that has 4 right angles must be this rectangle, if not a square. So you write to the big quadrilateral LOMP is a rectangle because it has 4 right angles. In the next step, we did another construction, that is to say, from point B, we do perpendicular on the radius OM. Again, from point B, we do perpendicular on the radius OM. So here this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. We define the touching point of the perpendicular from point B and OM. This point is point S. By doing this construction, the small quadrilateral SBQM. In the small quadrilateral SBQM, we have 1, 2, 3 angles, and therefore this fourth missing angle must be equal to 90 degrees in size, and therefore quadrilateral SMQB is a rectangle because it has 4 right angles. We know that the opposite sides of a rectangle are parallel to each other. Repeat again, the opposite sides of a rectangle are parallel to each other. So in the big rectangle LOMB, side LP is parallel to the opposite side OM. But LP is part of the straight line AP. So if a part of the straight line is parallel to another straight line, the straight line AP itself must be also parallel to the other straight line OM. Therefore AP is parallel to OM. AP is parallel to OM. In the next step, I copied those two parallels AP and OM, and also the diameter AOB in a new page, and we created 150 on the new page. So see, this is nice diameter AP, this is parallel to OM, AP is parallel to OM. This is the diameter AOB that touches the two parallels at points A and O. And actually, those two angles are defined as corresponding angles, and they are located between the parallels AP and OM, and therefore they must be equal to each other and their sizes according to Rule 50. So if the size of this angle is beta, then the size of this angle must be also equal to beta because they are equal to each other. So if you found out that angle PAO equals to beta, this is angle PAO that equals to beta, and then we also found out that angle MOB is also equals to beta. This is angle MOB is equal to beta. So in the right time, again SOB, this angle equals to beta, this angle equals to 90 degrees, and therefore this first angle must be equal to 90 degrees minus beta, according to the rule that the sum of the areas in the triangle is equal to 180 degrees. Likewise, in the right triangle ALO, this angle equals to beta, this angle equals to 90 degrees, and therefore this first angle must be equal to 90 degrees minus beta, according to the same rule. In the next step, we prove that those two right triangles can go into each other according to angle side angle rule. So why those two right triangles can go into each other? First of all, those two angles are both equal to beta, and therefore they are equal to each other. In addition, those two sides AO and OB, they are both the area of the second that is equal to R, and therefore they are equal to each other. And finally, those two angles are both equal to 90 degrees minus beta, and therefore they are equal to each other. So if we prove that those two angles and the side that is included between those two angles, that is R, are correspondingly, and this side triangle ALO are correspondingly equal to those two angles, and the side that is included between those two angles, that is R, in this right triangle OSB. And therefore, we shall prove that those two right triangles can go into each other according to angle side angle rule. We have those two angles, and the side that is included between those two angles are correspondingly equal to those two angles, and the side that is included between those two angles in the right triangle OSB. And therefore, those two right triangles can go into each other according to angle side angle rules. Okay, then I found out that triangle ALO can go into triangle OSB according to angle side angle rule. And from the fact that those two right green triangles can go into each other, we derive that side ALO, the right triangle ALO is equal to side SB of this green right triangle OSB. Why those two sides are equal to each other? They are equal to each other according to the rule that corresponding sides in the right triangles are equal to each other. Those two triangles can go into each other, and therefore those two corresponding sides must be also equal to each other in their lengths. So LO equals to SB. From those three, that LO equals to SB. So if we define the length of side LO as X, then side SB must be also equal to X because they are equal to each other. You know that the opposite sides of a rectangle are equal to each other. So in the big rectangle LO and B, side LO must be equal to the opposite side MPM. And side LO must be equal to the opposite side PM in the rectangle LOPM. But LO equals to X, and therefore the opposite side PM must be also equal to X units in its length. Likewise, in the small rectangle SBQM, side SB must be equal to the opposite side MQ, but SB equals to X, and therefore the opposite side MQ must be also equal to X units in its length. We already found out that PM times MQ equals to 36. PM is X and MQ is also X. Again, PM is X and MQ is X. So in total, X times X equals to 36. X times X is X squared, that is equal to 36. Here we took out of this equation and found out that X equals to the square root of 36, that is 6. So this is BM is equal to X is equal to 6, X also equals to 6. So in the next step, we implemented the Pythagoras theorem on this item BMQ. According to the Pythagoras theorem, BM squared equals to BQ squared plus QM squared. This one item BMQ, BM squared equals to BQ squared plus MQ squared. BM, the hypotenuse BM in the missing side, so it is, so it is BM squared equals to BQ squared. BQ is 4, therefore BQ squared is 4 squared, that is 16, plus MQ squared. MQ is 6, therefore MQ squared is 6 squared, that is 36. So total BM squared, that is the square of the hypotenuse, equals to 16 plus 36. Wait again, if you remember that BM squared, that is the square of the hypotenuse, equals to 16 plus 36. 16 plus 36 is 52. So here we took a look, so BM squared equals to 52. So we took a look from the equation and found out actually that BM equals to 50, square root of 52 units in its length. In the next step, we implemented the Pythagoras theorem on this big right line APM. According to the Pythagoras theorem, AM squared equals to AP squared plus PM squared. So again, according to the Pythagoras theorem, in the big right line APM, AM squared, that is the square of the hypotenuse, equals to AP squared plus PM squared. AM is the missing side, so we have to set it, so it is AM squared plus AP squared. AP is 9, therefore AP squared is 9 squared, that is 81, plus PM squared. PM is 6, that is, therefore PM squared is 6 squared, that is 36. So total, we found out that AM squared equals to 81 plus 36. 81 plus 36 is 117, so AM squared equals to 117. Here we took out all of this equation and found out that AM, let me say the AM equals to the square root of 117 units in its length. This is like AM is equal to the square root of 117 units in its length. So we found out that MB equals to the square root of 52 units in its length. Our task is to find out this green shape. The green shape is actually the right triangle A and B. You know that the area of right triangle equals to the base of the triangle times the height over 2. And therefore the area of this right triangle A and B will be equal to the base AB times the height AM over 2. Okay? The area of the green shape is actually the area of the green right triangle A and B. Is equals to the base MB times the height AM over 2. We only found out that MB equals to square root of 52 and AM equals to the square root of 117. And therefore in total MB times AM over 2 equals to the square root of 52 times the square root of 117 over 2. The square root of 52 times the square root, here we use the algebraic identity. That said that the square root of 8 times the square root of b equals to the square root of 8 times b. Therefore, the square root of 52 times the square root of 117 must be equal to the square root of 52 times the square root of 117 divided by 2. 52 times 117 is 6084. So in total, the area of the green shape, that is the area of the green right triangle A and B equals to the square root of 684 over 2. The square root of 684 is 78, and we have to divide it by 2. So total, the area of the green shape equals to 78 over 2, that is 39. So in total, we found that the area that we are looking for this question, that is the area of this green shape, that is actually the area of A and B, the right A and B, it is equal to 39 square units in size. Okay, again, the area of the green shape is equal to 39 square units in size. Okay, thank you very much.